let's learn about our final type of distribution for discrete data called a hypergeometric distribution. This one is quite significantly different from the other three we've looked at to date. The biggest difference is this time the trials are dependent on each other. In other words, as a trial occurs, the next trial will have a different outcome. In other words, the probability of success and failure changes from trial to trial. And because of this changing probability from one trial to the next, or from one outcome to a different type of outcome, we need to use combinations in our mathematics and our calculations. For a hypergeometric distribution, the random variable x will be defined as the number of successful trials. So it's not about a waiting period, it's about how many times do you get the outcome that you want. So the overall formula for the probability of a certain number of successful trials is equal to the number of possible ways you could have a successful outcome, which is A. Choose the number that are successful, and then we have the number of outcomes that are not successful with the remainder of the choices, or n minus x, divided by all possible outcomes and choose the number of trials. Okay, so I've tried to use some colors here to help you see the different positive and negative aspects of this formula, so you can see the successes and the failures and how they're substituted in. Furthermore, we can also calculate the expected value for hypergeometric distributions using this formula, where n again is the number of trials. We multiply by the number of successes we have over the sum of the total outcomes, or the total possible outcomes, positive and negative, successful and failure-like. So, I think one of the best ways to get going on hypergeometric distributions is to go through some examples and show you how this equation works. So in the first example of your note, we're going to go back to the scenario we had in the previous video, where we had a bag of nibs. Some of them were red, some of them were black, and you'll remember that there was a bit of a tease in the last time that we did this example, because when you reached into the bag, you had to put the nibs back. This time, we're going to allow you not to put the nibs back. In other words, you can eat them. So we're going to have 6 black licorice nibs, and we're going to have 4 red licorice nibs in this bag. And you get to reach in without looking, pick one out, and you get to eat it. And we are going to deem that getting a red one is a success, and that getting a black one is not a success, because, as everyone knows, the black ones are gross. The red ones are good. So red is a successful trial. So it says determine the probability distribution of the number of red nibs picked from the total nibs in the bag. So there are 4 altogether, which means that if we do a probability distribution, we have 4 possible outcomes. We could get, there should be, no, we're good. We can either get none, 1, 2, or we could get 3 if we're only doing 3 reaches into the bag. So let's begin by defining some variables. We're going to have the number of trials is going to be 3. Even though there's 4 red nibs, we're going to reach in 3 times. Don't want to be piggies. We're going to just eat a couple. Our success is the fact that there are 4 of them in that bag. And our failure will be, and I know choosing red nibs is maybe not so great when I'm showing you failures is red here, but we'll make it work. Failures would be getting those black nibs, or would be getting any one of the 6 ones. All right, here's our distribution table. Let's look at the number of successes that we could have. Okay, or in other words, how many red nibs can we get? And if we're going to reach in, choosing 3 nibs without replacing them, we could reach in and we could get none. We could reach in with those 3 draws, and we could maybe get 1 out of the 3 being red. We could have 2 out of the 3 being red, or we could end up getting all 3 of the 3 being red. Now, the probability of each of these events is equal to this equation up here. I decided to sort of put up in the corner so we'd have access to it. Okay, so we need to define, in this case, what is a successful event. Well, we've said that there's an opportunity for 4 successful events, but we're not going to have any successful events when x is 0. And that would mean then that there's 6 unsuccessful opportunities from which we have 3 minus 0. Or in other words, we pick all 3 black nibs. Okay, and we divide that by, come back to this in a moment, the fact that there are 10 in the bag, and we're going to choose 3. Okay, so this is the no restrictions piece on the bottom. If you plug all this in your calculator, you end up getting 1/6. So therefore, if we do the value of x times its probability, or x times p at x, we get 0 times a sixth, which is equal to 0. All right, let's look at what happens when you are successful once. So there were 4 red nibs from which you chose 1. And that means that there were 6 nibs in the bag that are black. You have 3 opportunities to choose one, and one of them was red, therefore the 2 that remain have to be black. Okay, and then divided by, again, 10 choose 3. No restrictions. When you do all of this, and you should try it, make sure you can, you should get a probability of 1/2. So 1 times 1/2 would have a value of 1/2 over here. Let's continue on. You reach in the bag and 2 out of your nibs are red. So there were 4 to choose from, 4 opportunities for success. You have 2 successes. There were 6 opportunities for getting a black one, and because you had 2 successes, that means that there's only 1 black one that you're going to end up with. Notice again that this plus this is going to be the total number of trials, right? 3 plus 0 is 3 trials, 2 plus 1 is 3 trials, 2 plus 1 is 3 trials. And again, over 10 choose 3. So, again, you should try this. Make sure you can get the math. You should get 3 out of 10. Last opportunity here. You reach in and you get scores, all 3 being red. Okay? So there were 4 red ones. You chose all 3 of them being red. There were 6 black ones, and you didn't choose any of the black ones. You did 3 minus 3, which was 0. Over 10 choose 3. And again, when you do all of this, you should end up with a value of 1 out of 30. Okay? Let's do this multiplication step. So 2 times 3/10 would be 6/10, and 3 times 1 over 30 would be 3 over 30, which we could reduce down to 1 over 10. Now we know that there are a couple of ways of finding the expected value. For all our distribution types, we can just add up the x times p at x values. Let's do that here, and then we'll compare it to the formula we have above. Now when I'm adding up all of these, I'd like them all to have the same denominator to make life easy. So this becomes 0 out of 10. This becomes 5 out of 10, 6 out of 10, 1 out of 10. So you can see I end up with 12 out of 10, or 1.2. Okay, so if I did this experiment many, many times, what it's saying is that on average, I would, if I picked out 3 nibs under these conditions, I would get a red nib 1.2. I would get 1.2 red nibs on average. Okay, now we know clearly you can't pick out 1.2, but that's what the average would yield. Now another way that we can do the expected value is using the equation up here, and let's see how that compares to what we did on the bottom. So it is equal to our number of trials, which was 3, times our opportunities for success, which there were 4, over our total number of opportunities, which is, of course, 10. 4 successful and 6 unsuccessful. So when we do the math here, we discover that we get 4 out of 10 times 3 is, I'll put it down here, 12 out of 10, which is exactly what we had down here. Comes out to 1.2 as well. So we can use either method to calculate the expected value for a hypergeometric distribution. Let's look at a couple more examples together. In our next example, again, we've got an aspect of randomness where we've got a box of thumbtacks and they have 2 colors of thumbtacks inside. And you want to be careful when you reach into those thumbtacks. 15 of them are going to be red, 20 are going to be blue. We're going to take out 10 tacks at random. We're not going to replace them, so we're going to keep them out because we're probably going to use them. What's the probability of drawing 8 red ones is our first scenario. So again, what I like to do is I like to lay out what are my variables, and then the next step is just a substitution process. So my number of trials, I'm taking out 10 tacks out of the box, so n is 10. Okay. A is our opportunity for success, and we're going to deem success as being drawing out 8 red ones, so there are 15 opportunities to pull out a red one if there's 15 red tacks in the box. We don't want to pick out blue ones. There are 20 opportunities to pick out a blue one. Okay? And then related to successes, our actual number of successes that we're going to have is 8. We're going to pull out 8 of those 15 red tacks. So let's substitute into our probability formula. Our probability when x equals 8 is equal to 15 opportunities for success. We choose 8 of them. We're successful to get 8 red ones. We have 20 blue ones, but we're only picking out 10 tacks altogether. So that means that 10 minus 8, okay, would be, we're going to have 2 that are going to be blue or unsuccessful. And no restrictions means that there's 35 tacks altogether from which I choose any 10. So again, make sure you can do this in your calculator properly. You should end up with a decimal that looks like this. You can multiply it by 100% to get 0.67%. So again, the context is 35 tacks altogether, 15 are red, 20 are blue. What's your probability of drawing 8 red ones if you only pick out 10? And it's pretty small. Okay, red is also the minority here when you're looking at the 2 colors. Okay, they're not there in equal proportions. Let's look at another scenario. What is the probability of drawing at least 2 red ones if you're going to draw, or if you're going to take out 10 tacks? So at least 2 red ones means that you could draw out 2 out of the 10, or 3, or 4, or 5, or 6, or 7, or 8, or 9, or 10. That is a lot of scenarios to look at and to add up all together. So instead of doing this directly, which you can do, but it's going to take a lot of time, could we do it indirectly? And the answer is yes. So the probability when x is equal to or less than, or sorry, when x is greater than or equal to 2, my bad. So looking at all of these scenarios, 2 and higher, can be done if we take a value of 1, we take away when x is 0, and we'll take away when x is 1. And what's left over will give us all of these scenarios. Okay? So another way to look at this, just so you don't start to get signs mixed up, is to do this. I'm kind of factoring out a -1 if you want to look at it that way. And let's put these guys together. And I'll show you why I want to do that. I want to do that because their denominator is going to be identical. And then it's also going to involve less punching in my calculator if I group it this way. So let's walk through. In the case of no tacks, that means that we had an opportunity for 15 successes and we were not successful. We chose none. That means then that of the 20 blue tacks, for my unsuccessful idea, I chose them all as blue. Okay, let's then look at the probability of 1. Again, 15 opportunities for success. I select one successfully, a red one. But that means then of the 20 blue ones, I must have selected 9. And then all of this is divided by our unrestricted scenario, which is 35 checks, choose 10. See how that's a little bit less work than doing each of these independently? Because you can do the numerator, hit equals, and then divide by the denominator and subtract it from 1. When you do this, you'll get a decimal that looks like this, approximately, and if you multiply by 100, it would be 98.5%, around that. So a really good chance of getting at least 2 red ones, and that makes sense, right? Because we've covered a lot of scenarios in that piece of math. So now, what is the expected number of red tacks for 10 draws? So what should you get on average if you did this over and over again in multiple experiments with the same conditions? Our expected value for x would be equal to our number of trials, which is 10, times our opportunities for success, which is 15, divided by our total opportunities, both successful and unsuccessful, which is 15 plus 20. Okay, so when you do this math, again, you should end up getting, and I'm going to sort of show it roughly here, 10 times 15 to be 150 divided by 35, and that comes out to 4.3. So you should expect to get 4.3 successes under these conditions, or 4 red tacks. We would probably round that down. All right. Now, can this scenario be used for times in life when you have more than 2 outcomes, either a success or a failure? Maybe you have 3 possible outcomes or 4 possible outcomes. And can it be extended into that? Well, life is like that too. And the answer is yes, we can actually extend it beyond just, I was going to say black and white, but in our case it's red and green. Okay? So here's how it extends. And I'll draw it out for you. The probability, and I'm going to show you why there are 3 different x values here, is equal to option 1 and the number of outcomes you have with that option. Option 2 and the number that you get for that option. Option 3 and the number you get there. And of course, all of these, x1, x2, and x3, have to be equal to n, your total number of trials. So let's put that here. Okay, that's important to know. That should equal your total number of trials. They have to get dispersed one of 3 ways if there are 3 different possible outcomes. And then your bottom is equal to the sum of all of your possible outcomes, which would be A plus B plus C. Choose n, or choose the number of trials. So it kind of looks confusing, but it's not really. The only thing that we've added in is this and this, right? Otherwise, what's remaining here is exactly the same as what we had before. Now, if you have a scenario where you have another outcome, possible outcome, maybe it's not just black or white, maybe you have 4 possibilities. You could add in another one. Okay, and in that case, all of these x values have to be equal to n. You'd have to add plus x4, and you could extend it beyond that. Okay, we're going to stop, but I will do one here where there are 4 options as an example for you. So our example is find the probability of drawing exactly 2 hearts, 2 clubs, 1 diamond, when you draw 7 cards from a deck. So, to put this into context, you've shuffled the deck and you peel off 5 cards off the top, or you pull them at random. What are your chances if you take 7 that you're going to get exactly this configuration? 2 hearts, 2 clubs, 1 diamond, and then the other 2 can be, well, what would they have to be? They'd have to be spades. Okay? So let's set this up. We have 4 outcomes. We have hearts, clubs, diamonds, and spades. And our possibilities for success, here A would be equal to, well, there are 13 possible hearts we could get, 13 possible chances of being successful for hearts. There would be the same number for clubs, the same number for diamonds, and the same number for spades, because there's 13 of each suit in the deck. What is the actual number of successes that we get out of those possible 13? Well, we're told that we get 2 out of 13. We get 2 chosen from the 13 for clubs. We get 1 chosen from the diamonds, and we get 2 chosen from the spades. Okay? So let's put it together. And you've actually done a question like this before in our combinations unit, just putting it back here in a slightly different context. So the probability of 2 hearts, 2 clubs, 1 diamond, 1 spade is equal to 13 choose 2, 13 choose 2, here's our hearts, here's our clubs, 13 choose 1 for the diamonds, maybe put a little symbol up here just so you know where I got them from, 13 choose 2 for the spades, all over, no restrictions, which is 52 cards, choose any 7. Okay. And you can punch this into your calculator and you'll end up with, not surprisingly, a pretty small percentage, because this represents a very, very small set of all possibilities of 7 cards you could draw out of a deck. If you multiply it by 100, you get 4.6%. And there you have it. Hypergeometric distributions concludes our study of probability distributions for discrete data. So the key here is to make sure you understand the criteria for each of them independently on their own, and then make sure you get to some review questions where it's all mixed up so that you can clearly pick out which tools to use in which scenarios. As always, if you have any questions, feel free to contact me.